talking about something called electrodynamics. So up until now, we've talked about electrostatics. Static means not moving. So we've talked about charges in one place. Dynamic means in motion. So today we're going to start talking about electrons or charges moving through conductors. Before we get started, I want to show you what your homework is so you can be on the lookout for how to do these problems. Number 1, define these 4 words: electric potential energy, electric current, and a closed circuit. And 2, use the symbols that we learn in this lecture to draw a circuit schematic for the following picture. So the lines here on this picture are copper wire, and it is hooked up to a lamp, a switch, and a battery. And you're going to make a much more simplified version of this using the correct symbols. So let's start with electric potential. Electric potential is based on the amount of potential energy that a charge has when it's in an electric field. So hopefully you all remember the term potential energy from when we were talking about falling objects. Remember, the potential energy of an object in a gravitational field is its mass times gravity times how high off our 0 point it is. Electric potential is very similar to this. When we move a positive test charge against the direction of an electric field, because remember, the electric field always starts on the positive and ends on the negative this way. If we move a positive test charge against our electric field this way, that's like picking a giant rock up and moving it upward off the ground. Both of those require a force, and it will increase the amount of potential energy in that object. Like with a rock that's raised pretty high up off the ground, this has a lot of potential energy, gravitational potential energy. And if you were to let go of it, it's naturally going to move downward. The height will decrease. It's the same with our charge here. If I were to let go of my little charge here, and remember that it's positive, it has some electric potential energy built up in it. Naturally, it wants to go toward the negative side. Now, electric potential energy and electric potential are not quite the same thing. They are related, but they are not the same thing. Electric potential is the potential energy per unit charge. So it not only depends on how far away from the negative terminal it is, or the negative charge, it also depends on how much charge it itself has. This is kind of confusing, but I'm going to show you a picture in a second that will hopefully clarify a little. We measure electric potential in something called the volt, which is represented by a capital V. And you've heard of this before. I'm pretty sure all of you have heard of the term voltage. Whenever you hear a voltage reading given out, that is telling you how much electric potential is present. Now, electric potential energy is measured in the same thing that all energies are measured in. Hopefully you remember this. It's the joule. So that right there will tell you that electric potential energy and electric potential are 2 different things because they're measured in different units. So let's take a look at this picture. We have our positively charged little Van de Graaff generator here. And because it is positively charged, that means it has an electric field associated with it. Remember that fields always start on positive charges and end on negative, so our field is moving outward. And it's pretty strong, so we want a fair amount of lines here. That's good. That's what our electric field looks like. Now let's imagine that we have 2 different positive test charges that we experiment with, bringing them close to this Van de Graaff. Let's look at this guy first. This is a positive charge, so it is going to want to move away from our Van de Graaff along the field lines. And it is the same distance away as this guy, which wants to do the same thing. So both of these have the same electric potential, but they have different electric potential energies. We know this because this charge right here is larger than the other one. So if you think about Coulomb's law, when you increase the amount of charge between two objects, the force between them also increases. So the force pushing this charge away from the Van de Graaff is going to be greater than the force on this guy. And that's because it has more electric potential energy. But if we look at how much electric potential energy it has per unit charge, so we take away the factor of how much charge it has, they have the same amount of electric potential. It's like picking up a really big rock off the ground and talking about gravitational potential energy. So the bigger the rock we have here, the more gravitational potential energy it has. But if we could ignore mass here, if we could take that out of the equation, like we can do for charges, you would find that the potential is the same. Hopefully that makes sense. If it doesn't make sense, ask me or ask Mr. Munson to help clarify. It's a very subtle point, but it's important for you to know that they're different things. So we aren't really going to talk about electric potential energy too much in this class. We're really going to be focusing on electric potential or voltage. And when we talk about electric potential, we really talk about changes in potential. So that means if we have an electric field from a positively charged object like we do here, and the green circles actually represent one charge. Our charge starts at point A, and then we move it to point B. We can measure the potential difference there. However, if we ignore this part and just say, okay, let's find out the potential of charge A, or the charge at point A, we cannot do that because there hasn't been a change in potential yet. So if we want to find the potential between points A and B, we take the final potential, which in this case is point B, and we subtract the initial potential. Remember, the change in anything is always final minus initial. So in order to do that, what you could do is find the electric potential energy at point A, subtract the electric potential energy at point A, and you would divide that by the amount of charge that your little charge has. Because remember, voltage or electric potential is electric potential energy per unit charge. You won't have to do this, but pointing it out. So we only measure changes in electric potential. Now, why am I telling you all of this? Whenever you have a potential difference between one point and another, you will have a flow of charge between those points. This happens in what we call a circuit. Now, circuits are awfully fun to draw, a lot of fun to build, and I think they're kind of fun in terms of the math you have to do. But to get started, I am going to show you all of the symbols that we use to simplify drawing a circuit. So if you were to wire up 10 light bulbs with wires and batteries and switches and try and draw a picture of that, it would be super difficult, especially for the artistically challenged like me. Being physicists, we want things to be very clear and simple and easy to draw and quick so that we can move on from the picture and on to the more important stuff, like the math. In order to do that with circuits, we need to define a few symbols. So, anytime you have a wire connecting two things, That's represented by a straight line. That is the easiest one. Anytime you see a straight line, that means there's a wire there. A switch is slightly more difficult, but not really. A switch looks like that. It's a wire with a break in it, which makes sense, right? If you were to imagine closing that little switch and connecting those, it then becomes a wire, which is basically how a closed switch acts anyway. So, a switch is just an open wire. A battery, which is what we will be using as a potential source in the class, looks like this. It has a long line on one side and a short line on the other. That is a battery. It's really important for you to draw one long and one short, because if you were to draw two equal sized lines next to each other, that's a capacitor. That is something different. So you need to make sure that your lines are uneven. This next symbol is my favorite one. A resistor is something that you add into a circuit to resist the flow of electricity, or to slow it down. We're going to talk about resistors in another video. But for now, anytime I tell you there is a resistor that exists in a circuit, this is how you draw it. You draw it as little monster teeth. It looks like that. And finally, a light bulb. This is mostly what you guys are going to be wiring up, although there are some other fun things you can add into a circuit. A light bulb is the X-Men symbol. It is a circle with an X through it. And as you notice, on the sides of all of these things, I have drawn lines. And these lines represent the wires connecting these objects. These lines are where you would connect it to the other elements in the circuit. So, for example, if I wanted to draw a very basic circuit with a wire and a resistor and a battery, this is what it would look like. I have a battery, I have a wire that is connected to it, and that is connected to a resistor somewhere. That's a basic circuit right there. You have three elements: wire, resistor, battery, resistor, and wire. This is a very, very simple picture to draw as long as you know the symbols, and they will become more complicated. But for now, that's how you use these kinds of symbols. So, what I want to talk about next is, where do we get a potential difference from? We, in this class, will mostly be using batteries. Hopefully you've kind of talked about batteries a little bit in chemistry class, but if you didn't, here's your short introduction. Alessandro Volta was a guy that discovered that electricity could be created if you had dissimilar metals connected by a conductive solution. This solution in modern day batteries is usually sulfuric acid, which is why it's really bad to break apart batteries. It's also important to recycle batteries and not just throw them into the trash based on the kinds of metals they're made of and the acid within them. We call one little setup like this with two different metals, in this case carbon and zinc, and an electrolyte in between, in this case it's acid. We call one of these an electric cell. So a single one of these is a single cell. The battery works by taking chemical energy and transforming it into electrical energy. This is kind of the same way that you can take gravitational potential energy and change it into kinetic energy. For example, raising a big rock off the ground and then letting it go. As it falls, its gravitational potential energy decreases, but its kinetic energy increases. Same kind of thing. We are just changing the energy from one form to another. So there are chemical reactions in this cell that make a potential difference between the terminals. And this happens because the acid slowly dissolves the metals. What happens dissolve both of these. And as it dissolves it, the electrons, or negative charges, will actually come off of the carbon, float around through here, and eventually be picked up by the zinc. Zinc really likes to get these electrons, and carbon likes to give it away. That's why the carbon side ends up with an overall positive charge. It got rid of some of its electrons. And the zinc ends up with an overall negative charge. Because one of these is positive and one is negative, there is a potential difference between them. If we connect those two terminals, we call them terminals, with something that conducts electricity, that will allow excess electrons to flow through it. And the flow of electrons through a conductor is electricity. This will keep happening until one of these terminals is dissolved. So when you have your remote control for the TV at home, and you pick it up one day and all of a sudden it's not working anymore, that's because one of your batteries died. That's the way that we talk about it, is a dead battery. And that happens because one of the metals in one of the cells in that battery is kaput. It is dissolved to the point where it can no longer do its function. If we connect several cells together, that makes a battery. But we now refer to a single cell as a battery too. So you could have a little battery that doesn't have a whole lot of potential difference in it. And that might be one single cell with one copper electrode and one zinc electrode and one little thing of sulfuric acid. That's a single cell battery. Or you can have 5 or 6 or 9 or 10 of them all hooked together, and that will make the potential difference stronger. That is connecting them in series, is how we call it. So when they're in series, you can add their potentials together. So one of these, let's say it's a AA battery, one of these has a potential difference of 1.5 volts. If we were to use them by themselves, we would only get 1.5 volts. But because we can stack them on top of each other in series like this, the total potential that we can get from these batteries is 3 volts. They add together. Now when we add this potential difference to a circuit, that causes current to flow. And like I said, current is the movement of electrons, or the movement of charge through a conductor. So electric current is the rate of flow of charge through a conductor. How fast does current move through that conductor? We represent current with the symbol capital I. So this is electric current. It's capital I. And we can calculate it if we know how much charge, so this is the amount of charge that moves through a current in a certain amount of time. So let's say we have 10 coulombs and it passes through a wire in 2 seconds. That is a current of 5. But 5 what? Well, we measure current in something called amps. It's technically called an ampere because it's named after someone, but we have shortened that to amps. You've most likely heard current explained in amps and not in amperes. And that is abbreviated with a capital A. So if we have 10 coulombs traveling through a wire in 2 seconds, that is a current of 5 amps. It's pretty simple, the math part. But don't be discouraged if you don't feel like you're grasping all of this. It's very, very difficult to understand, especially because we can't see electricity. We cannot watch these things happen. But here's an analogy to try and help. Pretend a wire is like a water pipe, and electricity is the water flowing through it. the voltage or potential is how much water pressure there is, or how much oomph is pushing that. The more potential you have, the more oomph you have pushing it. There will be more of a push. So if we have a 1.5 volt battery, that's not going to have a whole lot of oomph. It's not going to have a whole lot of push because it has very little potential. But if we have a 9 volt battery, that's going to have much more push to move the charges through the wire. Just like if we had more pressure built up in a pipe, that would have more push to move that water through the pipe. Current is like the water flow rate. So it's like if you could count how many gallons are passing by a certain point in your pipe per second, that is the current. In terms of a wire, that would be like counting how many electrons flow past a certain point in the wire per second, or how much charge moves through that wire per second. So now let's put all of this together into circuits. A complete, or what we call a closed circuit, is one where current can flow all the way around. It starts at one terminal and it moves through something that conducts electricity unaltered or unstopped all the way to the other terminal. So the actual picture of what this looks like is like this. We have our battery here, and the trick to drawing a closed circuit is to be able to start on one point and move all the way through the circuit without picking up your pen or pencil. So we can start on the battery, let me get a different color, start on the battery, and the electricity will move through the wire, through the light bulb, through the other wire, and back into the battery. I just made a complete loop without picking up my marker. That tells me this is a closed circuit. Now, this picture doesn't really look a whole lot like our schematic, but that's good. Look how complicated this picture is compared to this. This is much, much easier to draw. But it represents the same thing. We have a battery connected to a wire. The electricity flows through the wire and through the light bulb and back into the battery. So a little reminder of all of the symbols you will need to draw circuits. Wire is easy, it's a straight line. A switch is like an open wire. A battery is one long, one short. A resistor is the little monster teeth. A light bulb is the X-Men symbol. And then there are 3 more we didn't talk about before. Remember, capacitor is kind of, it looks like a battery, but these 2 lines are the same size. That's why when you're drawing a battery, you need to make sure you have one long and one short line. The circle with an A in it is called an ammeter, and that measures the amount of amps flowing through it in your circuit, so it tells you how much current you have. And a voltmeter, a V with a circle in it, or a V inside a circle, is how many volts you have flowing, which is the potential difference. How strong that oomph is to push the electricity through the wire. In order to get current to flow, there needs to be a closed circuit. And that means a path from one battery terminal through the circuit, the wire, and whatever else it's hooked up to, and back to the other battery terminal. Now, only one of these is a closed circuit. Let's see which one. So, we start on our terminal, and we can move through our wire, and here. But now, in order to get to the other terminal of the battery, I need to pick up my marker. That means this is not a closed circuit. That will not work. Let's try this next one. Start on the terminal, move up to the same terminal. Now, this looks like a closed loop, but in order for it to be a closed circuit, it needs to pass through from one terminal of the battery to the other. And this one never actually gets to the negative terminal. So that one doesn't work. Hopefully the last one will. We start on our positive terminal and move up through the light bulb, down through the wire, into the other terminal, back up. I did not need to pick up my marker to make a whole loop, and it passed through both terminals of the battery. This is the one circuit that will work. So when we have a flow of charge or a current, we conventionally say it's flowing from positive to negative. So we say if I were to draw the flow of current here, or the movement of electrons, I would say, okay, they move here from positive and around this way to the negative. But that's not quite exactly what's going on. Current is the movement of electrons, and we know that electrons are negatively charged. And negatives want to get away from other negatives and move to positives. So it turns out that the electron current, or which way the electrons actually move, is in the opposite direction. Electrons start on the negative because that's where they're built up. That's why it has a negative charge. And they move to the positive to try and dissipate that built-up negative charge. This all happened because Benjamin Franklin said, okay, we have two different kinds of charges, positive and negative. Later, when scientists were using circuits, they said, okay, well, we know we have two different kinds of charges. We have positive and negative. Let's just say electricity travels from the positive side to the negative. That's easy, positive to negative. But that's before we knew electrons existed. So at that point, they had already said electricity, whatever the heck it is, moves from positive to negative. But now we know electrons are what move around inside our circuit, and electrons actually move from negative to positive. The reason we don't fix it is because the original convention of positive to negative had been around for so long that it was really difficult to change. So we just left it. So we refer to these as two different things. Conventional current goes from positive to negative. Electron current goes from negative to positive. Sorry to be confusing. And finally, there are two different kinds of current that we can talk about. The really easy one to talk about is direct current. That means that current always moves in one direction and it is a steady flow. This type of current is produced in batteries, in static electricity, and in solar cells. So when you plug a battery into a circuit, that starts pumping electrons from negative to positive, and it does it in a uniform way. That is direct current. So if we look at the amount of current we have over time, it stays constant. It does not change. However, there's also something called alternating current. And this is the current that we get out of the wall outlets. The current varies. That increases from a maximum to a minimum. And it turns out it actually changes direction. So if we look at the pattern of our current, it flows in one direction, and then it stops, and then it turns around and it starts flowing in the other direction, and then it stops, and it comes back. It does this for us 60 times a second. So the electricity that we get from the wall changes direction 60 times a second. And all of our appliances, everything that we plug into a wall outlet, is designed to make use of this. So now that we have talked forever about electric potential energy, electric potential, current, and circuits, I want you to go back and answer these questions. If you need to use an outside source to look up your definitions, that's fine, but please include a citation.